So I promise you this will be the last time you will hear me today. The topic of my talk here is about the effect of hydrogen on the high cycle fatigue properties of austenitic stainless steels, mostly at low temperature. So this is a part of the PhD work of Romain Chauchois in a joint project between Institut Péprime in Poitiers and CETIM, located in Nantes and Senlis, mostly in France. So this is a brief outline of my talk. I will explain the motivation of the study. I will say a few words about the different techniques that we use. And then I will present some results. I will say a few words about the ratcheting in these materials during high cycle fatigue testing. Then I will talk about the fatigue life at different temperatures, and I will also discuss about the relation between ratcheting, mantle-citic transformation as a function of temperature. So, but the context of the study, I think it's no use to comment this type of diagram. Here, we are mostly interested by the transportation or the storage of liquid hydrogen. So it can be on a ship, on ground, but also, as illustrated here, in a case of a tank on board of an aircraft. And the particularity here is that we will have to take into account the cyclic loading induced by the filling of the tank over quite a large range of temperature and pressure during the service life. Just a few words about the liquid hydrogen tank. So the principle is that you have two shells with a vacuum between the two shells in order to limit the evaporation of liquid hydrogen. So the temperature of liquid hydrogen is 20 K. So that means that the temperature of the material constitutive of the wall here is about 20 K also. But depending on the filling of the tank, you can have a temperature gradient in the upper part of a tank. So it will depend, as I said, on the filling of the tank. It can be a few or maybe 20 K, additional K. And you have also to imagine some type of worst case scenario where, for some reasons, the tank could be placed at quite elevated temperature while exposed to hydrogen, and you could have a significant hydrogen uptake. Okay. So for this type of application, austenitic stainless steels can be good candidate as a replacement for aluminum alloys, as we have seen this morning. And the question is about the hydrogen embrittlement of these materials at low temperature. So I've seen you've already seen this graph in the previous presentations, where you have the susceptibility to hydrogen embrittlement of different grades of austenitic stainless steels as a function of temperature. And what is observed is that during slow strain rate tensile test, you have a maximum embrittlement around 200 K, maybe 190 K. And in addition to that, the magnitude of this embrittlement will be also highly sensitive to the chemical composition in relation mostly with martensitic transformation. That means that you have small embrittlement in a case of stable alloys. And in a case of less stable alloys, such as 3 or 4, for instance, you have a large embrittlement at this temperature. But the question is also, what about high cycle fatigue? So there are only very few data in literature. And on this topic. So we can mention the work by Ogata, illustrated here in the case of 304L austenitic alloy. So at this temperature of maximum embrittlement, you can see that we have a loss in fatigue strength at higher stress amplitude values. But if the material is fatigued at 20 K, you have no effect of hydrogen, meaning that the SN curve obtained in liquid hydrogen and helium are superimposed. So the objectives of our study were to assess the impact of hydrogen, either internal or external, but today I will mostly talk about external, on the fatigue life at different temperatures from 100 degrees C down to, let's say, liquid nitrogen temperature, with 2 grades of austenitic stainless steels, and try to get some insights also about the mechanisms controlling the fatigue resistance. So for this study, we selected 2 conventional grades, 304L, 316L. So this has been discussed during the some previous presentations, depending on the chemical composition, and in particular the nickel equivalent index. You can have different stability of the material with respect to strain-induced matensitic transformation that you can characterize by the MS or MD30 temperature, for instance. And so, of course, in our case, we have a higher index value, even if it's not extremely high, in the case of the 316 with respect to the 304. As regards fatigue testing, we used the ECOMAT test rig available at PEPRIM and different test rigs which are under development in CETIM. So for high cycle fatigue testing in air, we use the following conditions. Oh, sorry. A load ratio of 0.1. So that means that we have a positive mean stress, and this will be the cause of the ratcheting deformation. A frequency of 10 Hertz in order to reduce the test duration for this first screening. And for the results that I will present today, a temperature ranging between -83 degrees C and 100 degrees C. And typically the fatigue life that we target lies between 2×10⁴ and 2×10⁶. And the tests are rated as stopped in any case for this value of the fatigue life. As regards testing in gaseous hydrogen, so the loading conditions are the same, load ratio 0.1, frequency of 10 Hertz. So far, we have only data down to a temperature of -30. The pressure of hydrogen is 15 bars. So here you have an example of the pressure vessel during a test at low temperature. So typically, it's not a good idea to perform this type of test with the weather that we have today. Hot weather, a lot of humidity, you will mainly produce ice around the pressure vessel. So as I said, since we performed the test with a positive mean stress, that means that during the fatigue life, we'll have a progressive deformation. So here you have a comparison of this ratcheting strain as a function of the number of cycles for the 2 grades. And in the 2 environments at room temperature. And on the right-hand side, you have the data derived from these curves presenting the progressive strain rate as a function of number of cycles. And what we observe is that the progressive deformation is higher in the 316L, but the strain rate is higher in the 3 or 4L. And we cannot identify any influence of hydrogen exposure, which is not surprising because at this temperature, we cannot imagine that we have a significant ingress of hydrogen towards the bulk material. But what is important to note, however, is that in any case, you have, even at the very beginning of the test, a significant value of this deformation. So in these graphs, you have the variation of this final deformation as a function of temperature for the two environments. On the left-hand side for the 3 or 4L, and on the right-hand side on the 316L. So as expected, the progressive deformation is higher at elevated temperature than at low temperature. But it's difficult to interpret because, of course, you need a higher stress also at this temperature. And let me move now with the high cycle fatigue test results. Again, 3 or 4L on the left-hand side, 316L on the right-hand side. So here, basically, we compare the data obtained at room temperature and at low temperature, in that case, minus degree C. And so as expected, regardless of environment, we have a higher resistance at low temperature than at room temperature. And what we observe is that for the very long fatigue lives, we have almost no impact of hydrogen, but we need to apply stress amplitude above a certain threshold in order to notice a decrease in the fatigue life in presence of hydrogen, as indicated by the red arrows here. And you have the same here for the 316L. So here, presumably, we need to investigate higher values of the stress amplitude in order to highlight this phenomenon. Now, the same type of comparison, so the same data at room temperature compared to the data at 100 degrees C. And what is somehow surprising is that we have the same type of observation. That means that we have almost no effect of hydrogen at low stress amplitude. But if we increase this value, we have a significant loss in fatigue resistance, and this holds for the two grades. And this is quite puzzling to me up to now. I have no clear explanation. So one explanation could be that we have a barrier for the hydrogen ingress at low stress amplitude due to the presence of the dioxide layer. And that we would need to stress the material to a high level in order to break this oxide layer. But you have to keep in mind that you also have this high deformation. And generally, we also think about the martensitic transformation to account for the loss of performance at low temperature. And the point is that, as expected, at room temperature and 100 degrees C, we have no variation of the martensite during the fatigue test. That means at the end, we have the same amount. Of course, at low temperature, especially in the 3 or 4L, we have a significant increase in the martensite fraction. But it seems that this cannot account for the loss of fatigue strength observed at different temperatures. So this is a brief summary of what I've shown today. So we have no impact of hydrogen on the ratcheting and deformation. we noticed the hydrogen effect on fatigue life above a threshold in terms of stress amplitude. And it seems that matencytic transformation cannot account for the reduction in fatigue life, at least at room temperature and 100 degrees C. So we are still working on that. We have some tests planned at lower temperatures in CTM, and we will also perform some tests on pre-charged samples, and we will also investigate the deformation mechanisms and matencytic transformations at different temperatures using TEM and BSD. Thank you for your attention.